All right, how we doing, everyone? Doing good? You guys ready for this exam?
No.
Nope. All right. You guys miss me all? You know, the reason why I'm doing this review sessions because, well, one, it's kind of mid-semester, and I would assume, hopefully, Dr. Stevens is doing a good job in your lectures. And two, and it comes from the bottom of my heart, it's because, well, I've been doing 360 for signals and systems for about a year. Started last semester of fall 2020 with 360, and I can see some of you guys in here, and 361, which is spring of 2021. And now I was like, should it end there? I'm like, nah, let's try to see if we can do 480 for a little bit. So then the current students that I have, which are probably watching this video right now, could hopefully look at this notes one day. So for now, we're going to go over some 480 stuff. So there's some stuff I think I was hearing about. I think you guys are going to go over. One of the things you're probably going to go over, but I'll go over this, is the definition of, like, what do you call it? Impulse responses. Right? That's topic one, right? Is that something you're going to talk about in your exam? So he's going to say, okay, here's some H, something like that. Here's X and here's Y. And then what's the output of Y when this is H of N, X of N, and Y of N? What's output of Y?
The convolution.
Convolution. Oh man, if you guys don't remember, oh, you see the hands. If you guys don't remember that, then I'm kind of shaking now. How was your 360? Terrible. Oh man, I remembered. Yep. So the one thing I will look, and I have my notes right here, wink wink, is the way we're going to approach this first topic is I want everyone, because, okay, I don't know if you guys are in the 480 lab or doing anything, or I don't know what he's doing, but what I'm going to hopefully show you guys is we're going to treat this and we're going to try and build this system, okay? And you can build the system in the following way. You can either implement some kick, d of n, which is a delta function, or more specifically known as the Kronecker. So that's another way of saying the Kronecker delta. But when I do this, when we're doing a delta function, when we're kicking this box, or AKA, let me write this in a different marker, blue. Let's bring out the blue. You guys like these colors? AKA kick the box. Okay, this is what I'm calling it. We're gonna kick this box. Another way I'm gonna call it is, assuming there's no memory, we're doing a zero state response of this system. So when you're doing a zero state response, and if I were to probably implement this, I'll show you in another page. When we're doing a zero state response, state, another way to say state is memory, so these two are interchangeable. Zero state, zero memory. All you're doing is you're just kicking your box. When you convolve the Dirac delta, or the delta function, with anything, what do you get? Or you get the anything back. Okay? So if you want to know any system, you just kick it. When you put a Dirac delta or a Kronecker delta in your system, you'll always get H of N, assuming it's stable. So that's one of the topics I'll talk about. Another topic I'm just setting up a guideline. Let me just do this. One of the topics we're going to talk about is the impulse response. The other topic I'll probably talk to you about is convolution. Right? Convolution. Where, tell you now, I'll probably show you some practical implementations of that. So there's two ways. Actually, let me even look at my notes. Let's see. Oh, let's see these holy notes. Let's see. Where there's two things I'm going to show you. There's the mathematical way, where you're taking, let's say, some general signal. I'm going to call it x of n. All signals follow this pattern. They follow some amplitude, amplitude to the n, u of n. So, and then I guess this can be whatever speed you want it to be. Actually, the amplitude can also be complex. Can be complex. So all signals will follow this pattern. And you can do it the math way. You can go through your hard definition, which is like, let's see, from k is equal to infinity to k is equal to minus infinity, sum h of k, x of n minus k. Remember that? It's the raw definition of convolution. There's the math way. And then according to my notes, you're going to have drawing, where instead of doing this, you're doing the shift of, flip and shift method, where all you're doing is you keep this, or keep, and then you shift, or flip and shift. So this is what the practical meaning of this thing is. You're keeping some function constant, h of k, we'll call that, and then you're flipping it. Here's the minus k. That's what makes it a flip. And then the shifting comes from just shifting your n, or just shifting k, going ... So that's what you'll probably see on your exam. You're going to see both this mathematical way and then maybe drawing. But you don't have to draw. There's another way I'll probably show you. It's also on the whiteboard too. Actually, before I even continue, who else is in this class? Say hi, everyone. Yep, told you I got my studio monitors and everything. Yada yada yada. All right, and this is page 1. Don't want to forget that. But for now, let's talk about. Before we even talk about this, I'm going to talk to you guys about like the general definition of signals. So let's see. If I were to implement something, let's look at what I have here. So I just said that we have some system right here, x of n, h of n, and y of n, right? Where I'll tell you this. If you were to, let's say, okay, if I just define x of n to be any general equation, let's call it a beta of n, u of n, right? So beta can be maybe some constant or exponential. And then if you get the exponential, you can get a frequency, like sines and cosines, etc., right? So this is like the general definition. Okay? So this is what you're going to get. And then the same thing can be said with h of n. Let's say h of n is equal to, I don't know, some alpha of n, u of n, where it also follows the same rule. It can be constant, and it can also be exponential. So then what's y of n? Is, let's see, let me do this. Y of n is equal to, let's keep, let's do this. X of n involved with h of n, which is equal to, let's see, k is equal to infinity, k is equal to minus infinity, x of k. So I'm going to keep k for now. Guys, does it bother everyone? Good. And then I'm going to flip h. So to flip h, you do the k. So flip. Okay. And then to shift it, you do this n. Okay. It's a pretty bad n. That's okay. And then if I were to plug and chug our little equations that we have here, hint, hint, hopefully everyone's paying attention. Let me see if I can do this. Let's see. Is that better? It's okay, whatever. There we go. Where y of n is equal to k infinity, k of minus infinity. Let's see, what was x of n? All we're doing is we're replacing all the n's with k's. So bk u of k, okay? See that? Making sense? And then let's get our purple marker. And then for this one, here we have our n, right? Well, here we have our k. So all we're doing with this h of n is all these n's, we're just going to add a delay. We're going to add a shift. So to represent that, I'm going to do this h of, wait, no, not that. Alpha of n minus k, u of n minus k. Is everyone getting this? Is everyone clear? So how good is your guys' 360 memory? You guys remember how to get rid of these unit steps? Okay, because I'm trying to figure out how low to go, because if I go too low, it's probably going to take me too long. But you guys know this is a unit step, right?
Yes.
Okay. But this right here is delayed. Okay. So if I were to tell you this, if we have, what's the definition of unit step? U of 0 is basically equal to 1 when n is greater than or equal to 0, right?
Yeah.
And else equal to 0, n is less than 0, right?
Yeah.
So that means if we're trying to follow this rule, right?
So you can get rid of that u of k and
Yep.
have that k equals 0.
Yep. So that means this.
Before that is just going to be 0 anyway.
So this will affect that one, right?
Yeah.
Remember that? But then this one right here, this one here is a negative pulse if you think about it. But it's at some time n. So that means the minute this one hits k and n, if k goes to infinity, this is going to be a negative number. Okay? So if this goes to infinity, right? That means this will eventually have to be 0. So that means our bound that we have to respect is this n, which means this is where we change that. Is this clear?
Yeah.
Getting it? Perfect. That means we're going to have the following. Y of n is equal to, writing our new bounds, from k is equal to n. Is that how I want to do it? Yes, n to k is equal to 0, right? bk alpha of n minus k, and that's it. But we can pull this guy out. As you can see, we have our summation, but this right here doesn't belong. We can just pull that out. So we can do the following. A of n, summation n to 0, bk. Does it bother anyone if I do this? Nope, good. So then, do I want to show this method? Because I know how to do this, but I'm trying to, okay. So point is, this right here, there's a rule. There's a rule that you have to follow. Where if you have, rule, I'll just write it here. Where if you have your summation from, I'm going to write some crazy number, from n, right, to 0, okay? K is equal to 0, k is equal to n. Some alpha of k, right? This is going to equal 1 minus alpha n plus 1 divided by 1 minus alpha. Okay?
Because that's the geometric series.
Yep, the geometric series. Okay, just in case you wanted to look up that proof, because I had some people who were in like 480 saying, how'd you get them? Like, oh God. But this is going to take me too long to prove. But, okay, suppose this from here was like infinity, right? And then this goes to infinity, right? The condition for this one to be true, for this to be true, alpha must be less than 1. for this to be true. Because if it's something greater than 1, like 10, then 10 to the infinity power is infinity, it's going to blow up. But if it's like 0.1 to the infinity, then that's a really small number. So then eventually this disappears.
Yeah, it would just become 1/1.
Okay, so now that we know that, right? And we can convert this to alpha of n, and then we have we treat this as our alpha in a way, this right here, right? And we're just going to copy and paste it and then model this, okay? And we'll do the following. 1 minus b a, and then because our top bound is n plus 1, and then 1 minus b a. There you go. Which is equal to y of n. So if you wanted to know a general definition of convolution itself, convolution, for any two signals that are finite and stable, okay, you will always get this pattern, okay? And then if you take n to infinity, then this goes away and then you'll get this. Is that making sense, everyone? So, hint, hint, I already did this. Totally not on the exam. This right here?
Yeah.
Okay, good, because I'm just going over this. It's really simple stuff. Okay, and now let's look at what I have on the next page. All right. So now that you can implement this in math, right? We just figured out the general definition of convolution. Now there's another way of doing convolution, and that's by drawing. Okay. So you know how to draw these, right? So suppose I give you some h right here, right? It's going to be 1, 2, right? Just 2 signals long, right? 0, 1. And then let's say I give you, let's do a different color, an x, which is 1. Actually, no. Let's make this 1. Do I want to make this one 3? Now let's make x of n equal to 1, 2. Just going to be a length of 2. So this is 2, this is 0, and 1, right? So x of n, right? So there's one method you can do, and this is called the shift and, or not shift, it's flip and then add stuff, where if you have this right here, this is our raw signal, right? If you wanted to do an x flip, right? Where you would flip this on its bounds, right? And here's 0, here's -1, right? And then you would just flip this and just redraw it like that. And then all you would do is just look at the following above you. Okay, here you go. You have 0 right here, or 1 and 1, and then you can just add them. And this right here would go to here, right? But there's nothing there. So if I were to do the following, like, oh, here's our output y of n, right? Or drawing our y of n. If we have 1, so 1 times 1 is 1, plus 1 times 0 is 0. What's our output at y of 0? Just have 1, right? And then if we flip again, or shift it now, so x, flip, and then shift, I think -1. Go. Here we go. Here's our signal again. And then we just do the same process. See, and then you copy. Let me bring out a new marker. You guys like this material? Think it's helpful? Oh, don't worry. I'm just getting through the really introductory stuff. Oh, you never know. It might be on the exam. Okay, you get this right here, right? Then you would multiply this with this, right? That's 1 times 1 gives you 1. Plus, let's grab this light green marker. That times this. 1 times 1 is 1. So that means we have 1 plus 1 to give us, what's our y output at right here? 2. Okay? Then you start seeing this pattern where, oh, our thing is going to start shifting. And then you see this pattern. So the thing I'm trying to focus on to you, let's think of this as like an area. The area of this, if you were to look at this as like a 1 by 2 square, then what's the area of the square? 2, right? And then you realize, oh, if we just have our thing right here, it's just, here's 1, here's 2, and then it's another 2 right here, and then 1, and then 0. So if I were to do some crazy predictions, we'll see that, right? But let's say, and I'll give you guys this for fun. 2, 3, 4. And let's say the signal starts again. And how do you do that? All you do is just, well, you just flip it and then you just do the same process again. And you'll see a pattern. You'll see a pattern. Trust me, I think the signals are probably, actually, I think they'll actually be this long. And then all you do is just, you see this convolution happen and then do. Actually, let's even do it. So here's 0 and here's 4, right? And if we mirror this on the other side, we have -4. If I were to flip this right here, right? 0, 1, 2, 3, 4, right? Right? And then here's our x flip, right? So that means here's a 0 and a 4. So then if we put it through our system, let's see, this point would be -4, and actually let me just draw our actual h right on top of it. Here's h, right there, right? Or actually, no, this is wrong. This is wrong. Sorry. 0, 1, 2, 3, 4. There we go. Make sense? Everyone seen that? So I just, here's 0, here's 0, here's 1, here's -1, here's 4, right? I just flipped that all around. And here's our actual h. So our signal here, our 2 points right here are doing this right here, right? So when does this come into place? So if I were to shift this, okay, we have 0 times n is, time of n is equal to 0, right? So that means here we're going to shift it 1 here. Here's n is equal to 1, 2, and then 3. So that means it's going to start playing at this time. Is that how I want to explain it? Ooh, I think I gave you guys a bigger window. 5, 2. Let me try this. This one here has an n, h is equal to 3, and x is equal to 2. If I were looking at this, by the rules of convolution, ny is equal to nh plus nx, which is equal to -1, which is equal to 3 plus 2 is 5, -1, 4. So we have a length of 4. What I'm trying to say is, I think this signal might be a little too weird. I think I needed to cancel this one out and put it right here. The point is, suppose he gives you a periodic signal. You just do the convolution like that. Alright, let me see how I did it. He'll give you more space than what I have right here. So instead of this being like 2 length, 2L, this size right here is 2L, he'll probably give it to you like 5. So then you can play around with it, and your signal's probably going to be like 20 length long. So, hint. Okay? So now let me show you the math way, because I think the math way is much easier than the drawing way. So, suppose you had your h, right? And your h is 3 signals long. Okay? And there's a method that, well, I kind of discovered on my own, but it's also something you should have maybe discovered in 362, where you can do the raw definition of convolution, where, let me show you this. Raw def of convolution, where y of 0 is actually, let me do it. Y of n is equal to, let's go from, how do I want to explain this? H of n, x of k, n minus k, and I'm going to put a 0 here, and how long is h, n? No, I don't want to do that. Let's just make it k is equal to minus infinity, positive infinity. So what I want to try and get everyone's mind right now is, you see this h of k, right? This h of k will be bounded by, well, whatever this is, and some unit step. Actually, u of n minus u of n minus 3. I want to do that. 1, 2, 3. Actually, nothing exists below this signal right here, right? If I go to h of 1, right, we'll still have a signal. But if I go to h of minus 1, nothing exists there. So why am I going to sweep down to negative, well, k is equal to negative 1, negative 2, negative 3? So if I'm only bounded by h, then just stick with h. So that means the only k values I'm going to work with are 0, 1, and 2. 0, 1, and 2. So if I'm bounded by that, then I'm going to write this like the following. Okay, let's do this. H of 0, okay? H of 1, H of 2. All right? So now if I'm working at H of 0, right, and I'm working at Y is 0, N is equal to 0, then what's this? What's the value in here? If N 0 and K is 0, what do you have right here? X is 0, right? But now, if I were to do the sigma sum, so we're about to do the summation, if we're doing k is equal to 1, right? So here's k is equal to 1, but we're working y n is equal to 0, right? And what's our value here? And then you see a pattern where this one here becomes minus 2. Yes, there you go, right? So what I'm trying to get to you is, you see how these h's are flowing forward? Like it's going like, oh, you can actually see the signal itself. It's going forward. But then you see this right here is going this way, forward like this. It's like traveling backwards. Okay? So if you see this, like, okay, so now one thing I want to get to you is, if we're doing the raw definition of convolution, right? H of 0, H of 1, and H of 2 exist, right? Here's X of 0, right? Here's X of 1. What's the value of X of 1? Minus 1. Nothing. It doesn't exist. It just goes away. And same thing with this. X of 2 is gone. So then now the thing I'm going to try and really get into you guys' minds is, assuming we just have this right here, right? We just have a length of 2 and a length of 3, and we're trying to obey this rule of the size 4, right? So if you were to do the following, y of 1, y of 2, y of 3, right? You seeing what I'm trying to do right here? If we're trying to implement the raw definition of convolution, this is what you're going to practically do mathematically. Is that making sense? Are you following? Nope. So here's our 0 right here. Or let's think of this as 1, right? The next point, y of n is equal to 1, right? But if we're looking at h of k, right? But h of k only exists for 0, 1, and 2. There's no other values, right? But if we're at y is equal to n is equal to 1, right? And this is also a 1 right here, right? But we're only looking at h of k as 0, right? Here's a 0 right here, right? So that means our first point is going to be this h of 0 times whatever this is. And we have a 1 and a 0. What's this value right here? Seeing that? Or wait, let me see if that makes sense. Yes. You guys seeing that? So point is what I'm trying to get to everyone's mind is this right here, this here, this here, this is like it's fixed. It doesn't move. It just stays like this. We have our same signal all the time. The thing we're shifting is this. This one's flipped and switched. So actually, let me just finish this problem. If you were to look at this pattern, h of 1, are you seeing that pattern? Where if you wanted to do this mathematically, this is what you would be doing. The only thing you're changing are these little numbers right here. So this is x of 1, x of 0, x of minus 1. All right, and now here's what I'm going to show you. Here's x of minus 1, right? It doesn't exist. Cross that out. But we have x of 0 right here, right? It exists. And x of 1 exists too. So that means this is the signal that exists right now at this time, at n is equal to 1. And then this right here exists too. And now, you see how this right here is 0, minus 1, minus 2, right? This is 1, 0, minus 1. You see how this is like 0, 1, 2. This the pattern, all the pattern I want to show you is, here's this n, and this n right here is mimicked right there too. This n right here is mimicked right here. That means if you see that pattern, are you seeing it now? Is that making sense? And then if you were to look at this pattern, here's 0, here's minus 1, here's minus 2, 1, 0, minus 1, 2, 1, 0, right? And then 3, 2, 1. Right? And then let me show you the magic. So here's our x of 1 right here, and here's our x of 0, right? Those exist. Here's x of 2 right here. It doesn't exist. Let me write that. Doesn't exist. This right here. Right? It's just 0. That means this goes away, and then also this goes away, and this goes away too. So that means you see the signal right here traveling within our mathematics. So here's our signal right here. Oh, here's our 2 points out of our system. That's how you would do it mathematically. Is this clear to everyone? So this is the like raw definition, or you can do the drawing way. There's 2 ways of implementing it. So this is more for like the, oh, you recognize a pattern in the math, and this right here is more like, oh, you like to draw. So 2 ways of doing it, just in case he throws you a periodic signal, and hopefully you see the pattern too. Any other questions?
So this will be applied even if it's not like a nice looking signal, or like a nicer looking signal like that. Like say if we had our, I don't know, say like we had our x and n that look more like what our y is, and we're convoluting it with our h.
Yes.
We would still follow the same process.
Yep.
No matter what amplitude value.
Yep, and you can code this in MATLAB as in the following. So instead of this, you can just do this. H, which is let's see, an n by let's say nh size, cross product with x, which is nh by 1, and you would implement this in MATLAB back with matrices. So that's how you would implement this, and it will always work, guaranteed. I tell you that. And then all you do is just shift this, sample, and shift this, that x. So you get this weird thingy right there. Is that making much more? Is that making more sense?
Yeah. Yeah.
You keep this right here is fixed, and then you shift that. So the point is, you see all these h's are fixed. They don't move. The only thing that moves is this x, and this will mathematically work 100% of the time. I just discovered this in 360 when I was helping out my other students. But this is the phenomena that happens. Or you can just do it the drawing way, which is always nice to implement. So 2 ways of implementing this. Have you seen this on the other exam? You have? Huh. Okay, then I guess he's probably doing a really good job then. So 20 minutes?
It was very briefly. Not the specific drawing, but convolution was covered in the last exam. Correct. You're right.
Okay, so then just in case, I already showed you guys how to do this, but if he gives you a periodic signal, here you go. All right, next page. What time is it? 3:14. We should be okay. So now the next thing is, okay, now you know how to build this stuff, right? Or now you know how to like implement it in mathematics. Like now you're saying, hey, I want to build this stuff. Let's talk about it. So building. Okay, so the one thing I'm going to try and get to everyone's mind is, remember your block diagrams? Oh? Where there's the direct form 1, the direct form 2, and the transpose df2, right? Huh? Oh yeah, I think he's pretty cool, right? Or maybe he's pretty bad. Poor instruction. Yeah, there's a lot of Davids in this school too. I'm like, oh my god, there's like David A, David B, David C. I'm like, oh goodness, they're gonna start going into the Greek letters, right? Alpha, beta. Yeah, wonder what that puts me. Sigma. Just kidding. Okay, back to class. Where just to briefly summarize, where the direct form 1 has a feed forward block followed by some feedback block, okay? So this is direct form 1. It's direct. Okay, direct. As you can see that's the reason why it's the first block. It's just direct. Feed forward, feedback. For the direct form 2, however, we have the phenomena where we have the feedback circuits and then the feed forward circuits. All right? So it's kind of more like a saves memory, if you see it, and but harder to stabilize when you're thinking about noise. But don't worry about that. Don't worry. So don't worry about that. And then the transpose direct form 2 is this. Basically, okay, if we don't like the direct form 2, right? Because you don't want feedback circuits in the front. You like feed forwards in the front, because then the front end works, and then all you got to do is like fix the back end. But if you put the front end or the back end or these feedback circuits in the front of your front ends, then you're going to have oscillations here, and that's going to go through your output. And instead of the problems being at the back, it's the problems at the front, and you don't want that. So the reason why the transpose direct form 2 was like invented was, the best of both worlds, the best of direct, and it saves money. So the feed forwards are in the back or in the front, feedbacks are in the front, in the back, but it's more like direct, as in like if I were to show you like something really, really simple. B0, B1, and then A0, that's just a wire, A1 plus, and then it goes through some little block, plus, and, don't worry, but you know what I mean, right? It feeds like this. That's what we're looking at with the transpose direct form too, right? But for all intents and purposes, all these block diagrams, let me show you this. Y, Y, and Y, all these are the same. Give same output. And therefore, linear. Okay? So, if we're going to build impulse responses, we're going to try and go with this way because this is like the easiest way to visualize. So if I were to give you some type of circuit, let's call it like this. Should I give it to you? I'll give you a first order circuit. Y of n minus, should it be minus? Or should it be plus? Plus? No, actually, I'll make it plus. A1 y of n minus 1, right, is equal to B0 x of n plus B1 x of n minus 1, okay? How do you build this system? Okay, let's do it. Y of n is equal to, so what the output sees is going to be a B0 x of n plus b of 1 x of n minus 1 minus an alpha 1 y of n minus 1. So the way we're going to approach these block diagrams is we're going to build it with regarding y, so whatever y sees. So y sees a plus, plus, and a minus. So if we were to design a direct form 1 block of this, what are the feed forward paths looking like? So let me do this. So if we were to go down like this with a delay, right? We have one delay. Here's a B0. B1, right? Here's an x of n, right? And that's our feed forward circuit. Okay? And the reason why it's called a feed forward circuit, or aka a FIR, finite impulse response, is because if you put a Dirac delta in here, then when you kick it into your box, it flows this way. It just flows out into the output. Right? It's finite. It won't blow up. It just works. It's always stable. Okay? So if I were to tell you, okay, you're at an engineering company, right? Build EFF circuit. Okay, there you go. And then here's your C of n, right? So an impulse response, right? What's an impulse response? A response to an impulse. And what's the impulse, or what's our input then? It's an impulse. It's just a delta function. So if we're looking for this impulse h, right? The letter h. So that means the C of n, if we put a Dirac delta or a delta function here, the C of n is actually our h zeros. All right? Are you seeing that? We kick our box, and we're looking at the response of this box. What's the response due to this delta function? Or let me try to explain one more time. So, assuming there's no memory, right? There's no memory in our system. We have a 1 right here, right? That means what is our state right here? Just a 0, right? So if I have a 1 here, which is a delta of n, going into a B0, what's our output? B0 and then delta of n, right? And now I'm going to put now this delta function goes down here, right? And this becomes a 0, right? So this means 0 times b of 0, nothing, right? Well, here's our delta, right? So and multiplies to b of 1. So that means what is our output the next second? Congratulations, you just built your first part. Built first. Oh, my writing's so bad. Okay, so now, see how easy that was? Here's your age of zeros. And I will show you on the next page what I mean by building. Okay, 5. Right? So now, what is our output? C of n. There we go. You can plug in any input. So this could be like your unit step, or it can be your delta function, or any other function. Right? Is that making sense? So now what if I were to stress this out? What if this was the delta function, right? This is the delta function, so that means if we convolve this, anything with a delta function, what do we get back?
The same.
So you can now take this part, part, and you can put it into any other circuit. So if I were to do this following, let's put it into hz of n, hp of n. And we can put it into something like this. Are you seeing that now? So now what we did, what I'm trying to get to everyone is we just built this. Okay, we just built that. And now we have this poles right here. I'm going to call this poles, or our F feedback circuit. Okay? And so how do you build that? So if we go back to our equation, which is, let me see, y of n plus a1 y of n minus 1 is equal to b0 x of n plus b of x of 1 x of n minus 1, right? So if I tell you build me feedback circuit, how do you build the feedback circuit of this? Look at your feedbacks, your alphas, right? Which can be built as the following. You have a plus, and you have this big straight wire. Since we only have one feedback, right? I mean, D, right? But since if we were to rewrite this as the minus alpha 1 y of n, right?
So that'll give you minus a.
Minus a. And then I'll do this plus c of n. And there we go. Is that making sense, everyone? Mm-hmm. So here's y of n is equal to minus alpha 1. So this output sees a minus. And then we also see this input right here, right? Making sense already? Mm-hmm. So now here's the part where either you'll get lost or you will definitely understand this exam. So right now, just ignore this for now. Ignore for now. For now. Okay, we're just ignoring the zeros, okay? We're just looking at purely this poles, okay? We're just looking at this. All right, determine me the impulse response of the poles. What's the impulse response? Respond to an impulse. What's our input? An impulse. Right? Making sense, right? So, I just have an impulse here. We have a 1 here, right? So that means there's a 1 right there, right? So assuming no memory, so ZSR, no memory, okay? So that means what's the value here? 0. Okay? So that means the one condition I'm trying to force everyone to memorize for this exam is the condition you need to memorize is that time of y of 0 is going to equal to 1. And then y of minus 1 is equal to 0. And then dot, dot, dot. So y of minus n, however many poles you have, is always going to equal 0 for all for this feedback circuit. Is that making sense? So condition I'm going to get everyone to memorize. Conditions for feedback circuit impulse response, ZSR. Okay? That making sense, everyone? So then, okay, so let's say you wanted to solve for this system, right? And I'll show you guys on the next page. Go to page 6. Oh, I got you. Page 6. Let's see. So I'm going to rewrite this again. Zero x of n must be of 1 x of n minus 1. If you were to just look at the impulse response, right, of the poles, right, all you're going to do practically, ignore. And then all you're left with is this. How do you solve for y? So there's a trick. N minus n. Convert all the outputs, all the y's, to lambda minus n. The auxiliary equations, or some characteristic. Okay, characteristic. Right? So that means if you were to solve for this one right here, we'll get lambda minus 0 to the minus 0 plus a1 lambda to the minus 1 to 0, right? And now, oh, what's his name? What I'm going to do right now is I'm going to multiply this entire thing by lambda, so I can get rid of this weird negative 1 to give me lambda plus a1 is equal to 0. Lambda is equal to minus alpha 1. Okay? And now our guess for y poles is going to be in the form C1 lambda 1 to the n. Okay? So this is the guess we're going to take, where our condition, or actually, I'll just solve this right now, C of 1 minus a1 to the n. Is that making sense, everyone? And then how do you solve for this? Take this condition that we found. So then all you do from conditions, right? Then all you do is yp of 0 is equal to 1, which is equal to C of 1 minus alpha 1 to the 0. And that means y of poles, throw that marker away. Y are poles of n, the poles of this feedback circuit right here, I'll tell you right now, is our impulse response, right? So that means this right here is our h of poles, which is equal to minus alpha 1 of n. And this is what you'll look for. Congratulations, you just designed your poles. And now you can put this into any circuit you want. Your feedbacks, your feed forwards, another feed forward, etc. And now, put them together. Or, let me see, build feedback impulse impulse response. Okay? Is everyone getting this? And now let's go to the grand finale of this problem. This one's going to be a long one if he puts it on the exam. Come on. There we go.
I have a quick question.
Yeah, what's up?
So the H poles that we just calculated, can we also say that that is our zero input response?
Zero input response. Okay, I'll show you one more thing. Okay, actually, before I even talk about that, there's one thing I gotta add. U of n. Don't forget that, please. I promise you, please, don't forget that. Dr. Stiebert's a pretty crazy, well, not hard, lenient grader. He'll take -1, trust me. And then same thing for, well, actually, where's our feed forward circuits? Well, since this has a delta function, you don't need to actually worry about unit steps. The delta function is a rule on its own, so easy. You don't have to worry about that. But now we built our poles, right? We built our poles. So now what I'm going to try and get to everyone, for purely ZSR, the reason why I'm showing you ZSR before ZIR is because this is the hardest one, but this is the most general definition. So let's build the entire system together. All right, you see that system? Now we just put them together. Put together. Okay? So, what is the impulse response of this entire system? What is an impulse response? The response to an impulse. What is the input? An impulse. What happens when we convolve this with anything? And now this right here just gets transferred there. What is y of n?
Zero involved with H poles.
There you go. But note that y of n, so this is our input is an impulse. So what does this mean about y of n? It's the impulse response. There you go. And now you finally built your final circuit. Or this is a different y. There are two different ones. X of n, H of n. And now if he gives you a unit step response, a ramp or sinusoid, you're ready to take on any problem. Congratulations. You built that. So this right here is zero state response or impulse response of a system. Okay? So all we're doing is we're building parts. That's how I want you guys to treat this exam. You're just building these parts and then you can convolve them. So now I'm going to go back to what you were talking about, and let me see what page we're on. I'm going to assume page 7. Should have wrote this from the beginning. Right? So you were talking about ZIR, right? Which is zero input. Right? So for the zero input, I'll show you that right now. If we were to bring back our famous old equations, y of n minus plus a1 y of n minus 1, right, is equal to b0 x of n plus b of 1 x of n minus 1, right? if we have 0 input, what does that mean?
Inputs are 0.
Right? And that's it. And just get rid of that. And then I'll just rewrite this again, but hopefully it clicks in everyone's minds. And what does this look like? It looks like those auxiliary equations. Aux equations. And then you just do your process again. But there's a difference. 0 input doesn't necessarily mean 0 memory, 0 state. So there's memory. So this is Dr. Stubert's conditions. Where he's going to give you y of 0 is equal to, I don't know, 5. Or, for example, ex y of minus 1 is equal to minus 2. So he gives you this. An example. Okay?
Essentially the same process. Just
Same process, but he gives you this. So if he gives you something, you're doing a 0 input response. If he gives you some weird conditions like this, he's giving you a 0 input response. Make x is 0, and then you solve for this auxiliary equation, and then here are your conditions, your new conditions you gotta solve for. He'll give you this or any number. But when you're building this, when you're building your own system, your own direct, your blocks, your condition that you as an engineer need to memorize or figure out is this. This is always guaranteed. I'll tell you that with any system, digital system. This is always a guaranteed condition. Y is 0 is equal to 1. Make sense? Everyone getting that? So that means if I were to summarize a total response, let me do that on another piece of paper. Good thing I brought 30 extra sheets of paper. There we go. Yep. Let's see. Oh, another piece of paper here. This is page 8. If you wanted to do a total response, a total response consists of a ZSR, right? Well, actually, if you were to do the exam, start with the ZIR. Practically start with this. Make step 1, solve for the ZSR. Solve first. Solve for your ZIR, sorry. Where your ZIR is, here's your feed forward circuit, here's your feedback circuit, right? But your input is grounded. And then all you're looking at is memory. Okay? And then this right here gives you your YZIR. Okay? Is that making sense? So this is like the easy, really easy. Okay? Simplest one, just do auxiliary equations. Equations and whatever conditions he gives you. Okay? The other one is ZSR, which is just an impulse response. Okay? So actually this right here is like H of n, but we're not looking at this. We're just looking at the memory, so don't worry about this. Here's our feed forward circuit right here, right? Here's our feedback circuit, right? And all we're doing is we just kick the box. Look at that response. This total right here is the H of n. But for our condition, this is Y ZSR. And then how do you get the total response? Total Y, total of, and something like that. Does that make sense? So the reason why I was teaching you this first is any circuit, every circuit can be built like this. You building. You know how to build this. And now you know how to build this with the aux equations and conditions. And then this right here is memory. Okay? So I'm teaching you guys how to build these circuits. Now you can get this H right here, H of zeros. And here's H of P. Is that making sense? Now you can do anything you want. Now you can convolve this and get any output. Is that making sense? Is everyone going to get 100 on this exam? No? So that's how you would do it. And actually, let me see how he did it to me.
If we have any extra time, could we go over an example of doing the auxiliary equations with conditions? If we have extra time.
I don't know. Maybe we'll try.
That's okay. It's okay if we can't. That's something.
Because I only have like maybe. Well, we'll try it. We'll try my best. But I'll be honest with you. If you can just do this, you'll be fine.
Okay.
And a good example is just doing a second order. That means your poles are second order.
Yeah.
And then you just solve for, okay, if you wanted to, a second order equation. I'll give you an example right here. Y of n plus a1 y of n minus 1 plus a2 y of n minus 2 can be transformed into lambda squared plus lambda a1 plus a2. And you just solve for your lambdas. But he's going to give you simple numbers, as in easy numbers.
Oh, yeah, and then you just do it with the...
So that means he's going to probably give you, for example, like maybe... It's going to be really easy numbers, okay. Trust me.
Okay.
Like the Sham's outlines, there'll probably a lot of problems on this, but this is probably the worst it's going to get. He's not going to give you any sinusoids, I will promise you that.
Okay.
But if you just do everything I've mentioned, then you guys should be fine. You guys should be fine.
Cool.
Actually, let me just check one more thing. Yeah, that's it. Maybe I'll try something. I'll have to go over that at the end, but I'll show you guys. But yes, so that's the impulse response without using the Z transform. And yeah, he's going to say that. Okay, if you really want me to read it for you, solve for a difference equation without the Z transform. Because if you did it in a Z transform, then it becomes super easy. All you do is use the residue theorem and then get your pulses like that. So now the next thing I want to cover is, all right, so you've mastered how to build all this stuff. And now let's manipulate it. So one of the things he's covered is sampling. Okay, sampling. So how do I want to teach this thing without making it too complicated? So when you're doing any type of sampling, so let me see, a to d, x of t, x of nt, right? Or this right here, t of s is equal to, I would assume, nt, yeah, just some t right here, right? Well, actually, I'm just going to call this one f of s is equal to 1 over f or something like that, right? We're just talking about frequencies. Why did I do that? There you go. There you go. Much simpler, right? So when we're doing sampling, there's two things I want to force everyone. I don't know if you've been coming to class or if you dozed off. The most important thing is the Nyquist frequency. And this basically is defined as, okay, the rule is our Nyquist frequency, let me see, if I were to, let's just do it in practice. If I were to give you something like this, like some analog signal, x of, let's see, analog of omega, right? Then if you want to obey the rules, this right here has to be your F cutoff. Your F cutoff must be less than F of S over 2, which is equal to the Nyquist frequency. All right? So if you obey this, then you'll capture all your signals. It won't alias. It'll just stay bounded by this. So what I'm going to try and show you, everyone, and let's see, how do I want to explain this without getting too technical? Okay, I'll just try to show the technical versions. So what I mean by Nyquist frequency, so suppose I have in the time domain, right, some sinusoid, right? And let's assume that we are at the Nyquist frequency. So this right here is F, actually just F of, do I want to do this? So here's this, F is equal to 2 times the Nyquist frequency, no, F of n minus 2. So what I'm trying to get to, everyone, is if I were to sample this signal at the Nyquist frequency, I'm only sampling right here, and right here. So that means what's our value if I were to look at this on another plot? It's just 0, 0, 0. So if I were to sample at F of n, that means our output is going to be here, 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 right? Which makes sense, right? And then let's see. If I were to sample at a frequency faster than the Nyquist rate, right? Or faster, yes, faster than the Nyquist rate. So if I were to sample right here, right? And then right here, right? And then that's faster, yes, that's right here. And then you start seeing the signal right here, right? It's something faster. You still capture that data, so it just looked like this and this and this. It still captures your data. But what I'm trying to get to, everyone, is if you sample at something, so this is faster, F of S is greater than F of n, and then F of S is equal to F of n, and then where's my red number? If I were to sample here, right? But if I sampled something slower than the Nyquist frequency, so if I were to continue this, it'd be like this. F of S is less than the Nyquist frequency. You're going to start seeing this like slower signal. Let's see, like something slower. And that's going to look like the following. It's going to look like this, and you'll see something like that, and it's going to alias. Okay? Is that making a little more sense? I'm trying to figure out how to teach this without going too practical. You know what I mean? Is this making a little more sense? Okay. Let me try one more example, and I'm going to actually sample at the sampling frequency itself. Okay? This frequency here is the sampling frequency. Okay? What happens if I sample here and here at the sampling at the frequency? Yep. It's just going to be 0, right? But here's the conceptual part. What happens if my sampler was off by a phase? What happens if instead of sampling there, I was sampling right here? So our plot for this right here, I'll just draw right here. You get the 0 and you get the 0 right there, right? Okay, here's a time and here's voltage, right? What happens if I was sampling right here, right? You see this line, new line right there. And then this line right here starts looking like a DC voltage. Okay, so if you sample at the actual, let's see if I can mirror this right here. F of S, stuff here starts looking like DC. Is that making more sense right there? So if you started going too fast, this is too fast. this signal right here is too fast, right? Then you start making it look like, it literally looks like a DC signal. And then you can start figuring out like, oh, the stuff in the middle. All right, is that enough of the Nyquist frequency? Hopefully this is like, I'm like not going too in depth. I'm just trying to show you practically what we're trying to do. But now the next thing I'm going to try and get to everyone is, all right, how the hell do I do this on the exam? So, if I were to do this on an exam, if I were to give it to you, that one is page 9. This is page 10. So suppose I give you the following analog signal. Right? And it just goes down from here to, let's say, 1,000 pi, right? And then this is 1 volt, okay? So if I were to sample this, at the Nyquist rate, okay? So that means this right here is, okay, so to figure out our Nyquist rate, let me see. I got this for you. Let's call this right here. FC, that's our cutoff. That's what we want. FC is equal to pi over t. Okay, t of s. All right. So that means if this right here is 100,000, right? And there you go. That right there is our sampling frequency. Oh, there you go. See that? Not there. Better? So that right there is our sampling frequency. So there's a rule I'm going to try and get to everyone's minds. Is, let's see, how do I do this without getting too crazy? This is our new cutoff. We want to cut off right here, okay? So that means if I were to draw the spectrum, okay, here's x of t, here's x of nt, right? Or nt, right? Something like that, right? This right here is that spectrum. Then what's the spectrum of this? If we were to do a discrete time Fourier transform, the above here would be transformed to pi, and this amplitude here would be how do I call this? Let me see. 1 over t. No, this one here would be t. No, 1 over t. Sorry. There you go. And there you go. That's all. So your amplitude right here is 1 over t. And what's 1 over t? This right here is equal to 1,000. Is that making sense? And then this is our new cutoff frequency. Or this is like our bound before it starts mirroring into aliasing. So we're on the verge of aliasing. So if we sample too slow, then this starts going here, and we don't want that. And that means we start getting the weird aliasing conditions. And then, you know what that means, it just starts adding up here. And we don't want that. So if we were to, if f of s was less than f of n, then you're, let's say it's like right here. That means you start seeing this like plateau, and that's not good. Making sense? But right now we're just doing at the Nyquist rate. So now the next thing I'm going to tell you is, okay, and then this 1 over t comes because of how many points we're doing. So that's just our sampler, okay? 1,000 points, like per second or something like that, right? Making sense? So now, after we have our, okay, here's our A to D converter, right? I'm going to, let's say, let's see. Let's see if we decimate it. Let's decimate it. Okay, we're gonna decimate something. Let's just chop it in half. All right, so we're gonna take this signal and we're just gonna actually no, not decimate it. Let's do we want to decimate it? Actually, let's interpolate it. Okay? Let's speed it up a little bit. Okay, so interpolate. Okay, so what happens when we interpolate a signal? Actually, wait, before I even talk about that, actually, I think we have people who might come into this lab a little too later. Yeah, I knew no one would be here at 2:30, but hopefully I'm going to try and finish this. So when we interpolate a signal, right, we have all our data, right? Okay? But if I were to look at this right here, x interpolate, right? NT, right? Or I think LNT, right? I think that's divided by. If we were to look at this spectrum right here, this right here will look like the following. Pi over 2 pi, and then we get this falling signal. Is that making sense? And then our amplitude, because we're not really taking, let's see, let me see how we do it. Because we're still keeping the same points that we have, the amplitude here will still be 1 over t or 100 or 1000, right? That making sense? So now you know how to interpolate stuff. You just shrink stuff, but then you get this mirrored image. Mirrored image. So like you start seeing stuff like this. Or actually, let me interpolate this by 4. So if this was like 4, right? Then instead of this, you're going to get this. You're going to get the following. You're going to get this, 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 and this for your spectrum. Are you seeing that? So our thing just gets squished down. So this right here used to be, this right here correlates to this. So it just shrinks down. So this right here shrinks down to this if we have this condition, 4. Okay? Making sense? Yep, you're seeing all these other peaks. So this is unwanted data. Okay? So now let's put this through a filter, because I don't like that signal. 11. So let's say I give you, so that's our xi, that's our interpolated signal, nt, right? And I put it through some hz filter, right? And the filter I'm going to design you is, let's just keep pi over 4. All right? That's what I'm going to keep. So that means if I were to look at this orange signal, right? We're just looking at this right here, right? That means what's our output spectrum? There we go, and then up to pi. And then this right here is still 1 over t, right? And now, let's see one more thing. So now let's put this through some, now finally, an interpolator. Let's double it, or let's interpolate it. So we're gonna decimate. So that means we lose points. So what happens when we lose points? We lose amplitude. Okay? So that means if we decimate this by 2, all you're doing is you're going to stretch this plot right here. So instead of it being pi over 4, like that, or like that. Just like that. All right, but then this amplitude here just gets chopped up in half, so it's going to become 1 over 2t, which is equal to 500. And that's how you interpolate stuff, or decimate stuff. All right? And then yeah, I think that's about it. So I want to do one more thing. Actually, let's say he does you this. So let's say he makes you interpolate this by 4, right? Huh? Or decimate. So it goes down. It's just we chop 4 points or every fourth. So let's say it's by 4. So instead of this going like this, it's actually going to be like this. Okay? Like that. And this becomes 1 over 4t. All right? And then there's one more thing I got to show you. So let's say at the end of the exam, he does this and says, okay, um, let's put it through some multiplier. And we're going to shift this by, let's say, e to the minus j pi. All right? So I'm looking at this green signal for now. Okay? And you know that if at this Nyquist frequency and f of n, this n pole, stuff has to periodically shift or has to repeat again, right? So this right here, you just shift everything by pi over 2. Sorry. Easy. Yes. 1 over pi. Actually, does he call it that? No. Not pi over 2. Yeah, sorry. Pi, because I was thinking about minus 1. Okay? So when you see this, all you do is you just shift your plot. Just shift it this way or that way. Is that making sense? Decimating, interpolating, shifting. Easy? All right, boom. That's another couple points there. And oh, it doesn't change. It doesn't change amplitude. Just shifts. Okay, same.
Yeah, because that's all that exponential is just a shift.
Just a shift.
Yeah, whenever you see an exponential like that, you know it's just a delay of how.
All right, and then that's all. And he can give it to you in any order. Maybe he's gonna give it to you as in like, oh, he'll give it to you like he'll make this one go up. Then he might give you, maybe he might actually give you the shift early. Then he might give you an decimator like this, right? Then an H, something like that. Or he might give you, maybe he might make you do this, and then go through a filter or something like that, H or something like that. So there's many ways of doing it. He can just mess with you. So interpolate, and then decimate, then shifts, and then filter, H. So stuff like that. And then if I were to show you one more thing before I wrap this up, oh God, hopefully this is not too long. What if he gives you the following? So x of a of this is this right here, right? Which is fc, right? Pi. Okay, let's just stick back to our example. And what happens if he does twice the Nyquist rate? All right? Or 2 times f of n. Okay? So that means if you were to sample this, remember that I was going to show you MATLAB code, but remember how if we were sampling at the Nyquist frequency, we keep this as like our pi, but now since we're sampling too fast, then our new signal is going to look like this. And is that it? Yes. And there we go. And this becomes 1 over t, but let me see. It'd be 2 times f of n, which is equal to 2 times, let me see. Give me a moment. So it becomes 2 times, oh, give me a moment, I save everyone. 2 times that, by, let's see. Oh, sorry. Is equal to pi over t, right? That means t is equal to, yeah. T is equal to 2f. 2f, not 2f. Flip this, cancels with that. Okay, let me solve for this. 2 times 100,000 pi is equal to pi over t. That cancels with that. T is equal to 1 over 2,000. Okay, there we go. And then this becomes 2,000. Making sense?
A little bit.
All right, so just in case he changes the frequency on you, now you're ready for that. And then if he makes this, huh? I think it's going to be graphic. It's going to be graphic. He's just going to make you mess with the spectrums. But I think the hardest part is figuring out this and how to start with this. Box equations?
Yeah.
Sampling in the time domain, sampling in the frequency domain?
In the time domain is n times t, but in the frequency domain there's a formula that's not as
I think I know what you're talking about. Oh, I would have to see it. It's clicking onto me. But actually, let me show you what I was trying to do with this one right here, right? Actually, let me show you guys a MATLAB code. I don't even know if there's supposed to be people coming in here. Because there's like some dude over there. And today is Nevada Day, so I'm like trying to figure out.
I didn't have a lab today. I usually have a lab at 8:30 in the morning, but it was not happening due to that day. So.
Let's see. Let me see if I can run you guys some code. S sampling. Nope, no. Let's figure out plot. Let's see if this runs. Ah, yes. So I have some signal right here, right? And then let's sample this at the Nyquist rates. So this right here is some time. I'm just giving you some like signal right here. This is an actual time function. So t, right? Here's your t and here's your seconds, right? And I was like, oh, okay, let's sample it at this. So I'm gonna do the following. I wanted to get to something. Sample it at the Nyquist frequency. Show you that. So if you sample at the Nyquist frequency, you're not going to get enough data. But if you sample much faster, what I'm trying to get to everyone is this. Hopefully this makes sense. See that? There we go. So this is our analog signal. And then I just sampled it at 10 times the Nyquist frequency. I just changed it by 10. And then if you start sampling it too much, like let's say 20, then it starts looking like it's slower. So that means it gets squished. It looks like if you start sampling it too fast, then it just starts squishing down to the lower frequency. So
you start to lose data.
No, you get too much extra data, but that means your precision is much higher. So instead of your maximum frequency to sample being 1K, now you can sample like noise, like 1 megahertz. Mm-hmm. So that means whatever let's say your sampler is like 1K, right? Like your highest frequency is 1K, your highest Nyquist frequency is 1K. So that means, your highest resolution is 1K. But let's say you increase your resolution from 1K to 1 megahertz. Now the 1K gets squished down here, and then the megahertz becomes your new like resolution.
Oh, okay.
But then you have to increase this thing. So everything just gets squished the higher you sample. Mm-hmm. So it means you can just sample higher frequencies. But then all the middle frequencies become squished. Okay. Pretty cool. So that's exactly what I try to get you. But any questions on that one? Okay, because there's one more thing I got to talk about. And this is the final part. So there's one thing Dr. Stubert mentioned. And let's see. Which page is this? Oh, I'll figure that out. What page is this? 5, 6, 7, 8, 10, 11. I think it's 12. I was just going to say 12. So final question. Fourier transforms. Okay? So One thing I saw on your guys' exams was, let's see. Oh, how do I want to explain this? Let's see. Let me remember. Y of n. Remember y of n is equal to some convolution infinity. K is equal to minus infinity of h of k, x of n minus k, right? So, assuming that if you have a Fourier transform, there's one thing he was trying to get to you, and he was trying to do these like in classes. I don't know if he's doing that still. So, yeah, periodic stuff. So when you have periodic stuff, one thing I'm trying to get to you guys, everyone, is suppose your x input is equal to, I don't know, some e to the j omega naught, let's see, of n, right? What does this look like in the Fourier transform? So or let's say, yeah, let's call it f, right? It's just gonna equal, let's see, 2 pi f naught, right? F, there we go. It's just gonna look like the spec. It's just gonna look like, well, it's an amplitude of 1, just some delta function in the Fourier transform. So the cool thing, and I'll probably show you guys this little proof. Let's say we input this into here. Let's call it e to the j. Let's see, pi over 2. Let's just put that as an example. Infinity to minus infinity of h of k. Let's say e to the j pi over 2 n minus k, right? I'm gonna convolve this right here, this signal, with our h's, right? So doing this, let me see if I can show you something cool. Let me see. See this n right here? Right? Oh, there we go. You see the n? We can take it out of here. So that means we have to fall on e to the j pi over 2, right? N. Okay? And then our leftover equation, infinity to minus infinity of h of k, e to the minus j pi over 2k. But there's one thing he was trying to stress out when you see something like this. Like that, remember that stuff? But then we have this right here. So there's a thing in the book I was reading where if you have something like this, e to the j, like omega or something like that, omega naught, this is your omega naught, you can transform this easily into e to the j pi over 2 n, which is your signal itself, x of n, right? That's our original signal. And then you have your h, e to the j omega, where omega is equal to pi over 2. So you know what that means? You know what this means? All you do is if you solve for your magnitude of h e to the j omega, and then find the phase, actually the final answer would be this times e to the j pi over 2 and then e to the j angle of h, right? So you're going to have a magnitude. Oh, oops, I should probably get rid of that. There you go. Make better? Mm-hmm. And phase. So what I want to get to you is, for any system, assuming your input is periodic, all you do is whatever your periodic signal is, you just punch it into here and punch it into here. You find the magnitude at whatever the input's at and the phase at whatever the input's at, or the speed of the phase. You know what I mean? that making a little more sense, or you guys want me to try something? Let me try.
Try something.
13. Let me try this. Okay, one more example. If I were to give you following, let's see. Oh, oops. Y of n minus a1 y of n minus 1 plus a2. I'm just creating my own numbers, or actually let's keep it plus a n minus 2 is equal to b0 x of n plus b1 x of n minus 1 plus b2 x of n minus 2, right? And if you were to find the Fourier transform of this, which is basically h of e to the j omega, which is equal to y of e to the j omega, x of e to the j omega. And I would assume everyone knows how to solve for that, right? All you do is you replace your y of n's with, let's see, let me see if I can find the rule. Y of n minus n, I'm going to call it that. And what did I replace it with? You replace it with e to the minus j n omega. All right? That's the rule we're going to memorize. Rule. When we're doing a Fourier transform. So that means if I were to rewrite this again, this would be, before solving for that one, we're going to do 1, or actually not 1, e to the minus j0, okay, plus a1 e to the minus j, or minus j omega, right? Plus a2 e to the minus j2 omega, right? That's our y's, okay? Okay? And then let me see. Actually, oh wait, there's one more thing I'm forgetting. And y of e to the j omega, there we go. Oops. Forgot to tag that on. And let me try this. There we go. Is that making sense? All right, and now this is equal to, and the x's, we do the same thing too. X of n minus n, replace this with x of e to the j omega, e to the minus j n omega, right? So that means for this one, we're going to do b0 e to the, let's see, e to the minus j0, right? Which is just ultimately 1, okay? Plus b of 1 e to the minus j omega, plus b of 2 e to the minus j2 omega, right? All multiplied by e to the x to the j omega, right? Then you see this right here and this right there. You can plug this right there. You can plug that right there, and you can do some weird things, and I'll show you right here. Actually, let's solve this right here. There we go, right? So here's our poles, right? Here's our zeros. If you see the trick, b0 plus b1 e to the minus j omega plus b2 e to the minus j2 omega divided by just 1, sorry, plus a1 e to the minus j omega plus a2 e to the minus j2 omega. And there you go. And now you remember how to do, and actually let's do it on another piece of paper. So now you have your total h e to the j omega. There you go. And then what I'll tell you now is, let's see. I got this. Okay, I got this. There's one thing I want to try and see if I can show you guys. Let me see. I'll show you this. So if we have y e to the j omega, right, which is equal to h e to the j omega, right? Right? And then let's see. Let's try to evaluate this. Is that what I want to do? Evaluate this at omega is equal to pi over 2, okay? And then x of e to the j omega. Remember how I was saying that in the spectrum of x of n, right? Of that signal right here is just right there at 2 pi f naught, right? So what's the spectrum of, in terms of mathematics, x e to the j omega? It's just a delta function, right? Delta of omega minus pi over 2, right?
Yeah.
Because that's where it happens. E to the j minus j, no, positive j. No, positive j. Right? This is where it's going to happen. This is our frequency. Right? But then there's a weird rule that he goes over in his notes where you have to put a 2 pi right in front of that. So 2 pi of a delta function. This is your value right there, 2 pi. Okay?
Why do we have to put the 2 pi in?
So there's like a weird thing he goes over in his notes, and I read it. It's like a 5-page proof. And it's
in his book?
In his book, yes.
Oh, okay.
It's 5 pages long. He says it's easy to convert from, from this to the time domain. No. From the time domain. So it's easy to see one frequency and transfer. He says it's easy to go from time to the frequency domain. Easy to see this, but it's hard to go from F to T. He says it's hard, or something like that. It's a weird proof. It's a proof. Just memorize this. Memorize this. I think he goes over that in 361. I don't know if you guys remember that big proof. Yeah. So point is, he told everyone to memorize this. This is what you're memorizing.
Okay.
So that means, what do you replace this with? There you go. And then all you do is you just evaluate everything at, let me see. You evaluate this entire thing with that condition that I just mentioned, pi over 2. So that means this becomes b0 plus b1 e to the minus j pi over 2 plus b2 e to the minus j 2 pi over 2, right? All divided by 1 plus a1 e to the minus j pi over 2 plus a2 e to the minus j 2 pi over 2. The reason why I'm keeping that 2 is to follow our little guideline right there. You can simplify as you want. And then multiply this by your 2 pi omega minus pi over 2. Alright? And then this should give you, let's see, what's he do here?
Good question. Why are we evaluating at omega equals pi over 2? Is that just a value you pick?
No, that's our frequency. That's our input frequency.
Oh.
It comes from input frequency. That comes from our input frequency. And then let's see. I'm trying to see if I can try to get this for you. Let me see. Is that how you want to do it? Let me see. I think he might want something different. No. I got this. You evaluate this, then let's see. +1, +1, +1, +1. I should be putting numbers in there to make it more easier to see. What I'm gonna try and tell you guys, everyone, is if you try to evaluate all this numbers, this will give you really nice numbers. I'm gonna try and tell you that right now. No, I don't like that method. I want to show you another method. Let me show you a mathematical way. Let's see.
Would it technically be wrong if we just kept that as the answer?
No, I don't know, man. Okay.
I mean,
Okay. Let's go.
No, but you probably shouldn't.
Let me go my method, because the way that someone else taught me is kind of weird. Let me go with David's way. I like it math. They were trying to teach me how to do it the drawing way, and I was like, I don't want to see it. All you're doing is just this. And then, since your input, let's do this x of n, but x of n, and then you multiply whatever frequency this is. Let's see. E to the j, hold up. Pi over 2, that's our frequency. And then all you do is multiply this by the angle. So plus h of e to the j omega is equal to pi over 2. You just solve for your actual thing. You just solve for the magnitude, so you just force punch in this number. So this right here, or actually, yeah, that's it right here. You just force this number into here. And then here's your input right there. Here, right? That's your input. And then all you do is you just solve for your phase, whatever phase this gives you. So this is going to give you like, well, you'll have to find that out. It'd be easier with numbers, but I'm already stretching already to like 2 hours. But point is, all you're doing to find the output is magnitude, phase. That's as best as I can try to teach you, but it's a lot of information to pack into like 2 hours, man. I wish I had more time, but I'm already pushing it to 2 hours, man. I'm already getting hungry. 16. But is that making sense, everyone, or maybe a little clear on what to expect on this exam?
Yeah.
So, things to expect. Huh? ZIR, ZSR, and the Z domain?
Yeah.
You guys have to do that? Okay, tell me what you got to do. ZIR, ZSR, and the Z domain. Well, I can tell you this. If you had our... Okay, wait. Before I do this, Z transforms. So it's the same as Fourier transform, but your new rule is y of n minus n is going to change into y of z, then z to the minus n. That's all you're doing. And then
But it's the same process regardless.
same process regardless.
Since the Z is pretty much a Fourier transform.
Yep. And then all you got to do, and I think one thing for the z transforms, you have to use partial
Partial fraction decomposition or expansion.
Or expansion, where you have like let's see how do I do this? I'm trying to see if I can give you poles. 1 plus z minus 1, 1 minus z minus 1, b plus z minus 1, or no. No. That's bad. That's really bad. That's really bad. Sorry. There's a thing I remembered. 1 plus b1 z minus 1. Yeah, I remember this. Oh, it's clicking. And then something plus alpha 1. I don't know. Z minus 1. I'm just coming up with numbers. 1 plus q. Just numbers. Where you need to get this into forms of a 1 plus. I don't want to make this a.
Plus b of 7.
Let's call this one c. I'm just calling it some random numbers. Just think of it as numbers. cz minus 1 plus b1 plus qz minus 1. Where if you remembered, there's a thing, I think I remember it. The unit step function, the z transform of the unit step is equal to 1. Let me remember this. There's a z plus 1 or 1, or is it z plus 1 or z minus 1? Z minus 1. I think it's this.
I think both of those are correct.
Questionable, but this. Your objective is to get something similar. Make this mimic this.
Yeah, we're essentially solving for A and B so that we can then split them and then do the inverse of the Z transform to actually get them.
It just clicked on me like really huge. It just clicked. So what happens if you have some alpha of n, u of n, right? And you do the Z transform of that. Alpha, is it, yeah, Z minus 1. There we go. So all you're doing is you're trying to find these like numbers here. And then if you wanted to turn this back into the time domain, all you do is just chuck this right here, a to the n. And then since this is the unit step, this right here, and that's the reason why we do this residues. This right here is also known as residue. Okay? Simple enough?
Yeah.
So, okay, I didn't know that you guys had a Z transform. My previous little notes.
Yeah, we just talked about we're going to do it both possibly.
Oh, God, I'm so sorry, everyone. But point is, if I were to teach you this, please do partial fraction expansion, and if you see something that mimics this, then you know how to transform this into the time domain. Done, boom, and then plus q of n, u of n, ... Simple as that. So things to expect. Z transforms, Fourier transforms, impulse responses. And I don't think he's going to trick you. I think he's going to just give you a ZSR. That's probably the worst case scenario. And ZSR is a lot of work. It's a lot of work. So all that stuff I was doing is a lot. ZIR is much, much easier than ZSR. So it's just an impulse response. Just kick your box. And then sampling. Drawing. Okay? And then the final topic, or the other thing I was talking about, was just maybe convolution? Maybe? I don't know. But holy crap, man. There's so much things I can just fit into 2 hours and 7 minutes. Man, if only I actually taught this class. All right. Any other questions? That's a conversation for another day. All right. Have a good day, everyone.